Hello, in this lecture we're going to do some applications of tunneling to show you how many effects are actually explained by these important quantum phenomena. If you remember, tunneling is when particles they can pass through barriers that classically they could not pass. And we explore the nature of the tunneling, which is due to the quantum nature of the particles, right? And because of the wave equation, because they are wave in nature, that's allowed for them to have a penetration, and then if they can survive in the other side of this barrier of potential, that means they tunnel. Okay, so we explain and we even deduce some relations that allow us to calculate what is the tunneling probability, right, of any barrier by adding rectangular barrier, making any barrier we want. And then we made an integral, and we came with a very nice solution for that. And just for you to recall that the expression of the tunneling, you know, if you remember, we did a barrier of any generic form v of x, and then we were able to come with this expression for the probability of transition. Of course, if I multiply the probability of transition by the frequency in which a flux of energy, a flux of particles is coming to the barrier, means that we're going to have what is the transmitted flux. Because actually probability is the ratio between the transmitted flux by the incident flux. So this probability can be written as the modulo of the transmitted flux. That's a concept that we must see very soon, and the transmitted and the incident flux. This is the probability, right? And then we can know what is the rate or what is the number of particles that can tunnel to a specific situation. We're going to now make some applications. There are many atomic phenomena and nuclear phenomena that relies on tunneling. And then there are some biological phenomena. You know, we have tunneling membrane, tunneling charge transfer in important process. So many tunneling, in fact, is happening now in our body or in any living object. We believe that tunneling is actually responsible for many important things that happens around us. Well, the first example I'm going to give you, which is a textbook experiment or example, is the tunneling through conductors. You know, when you have a conductor, we all learned that we have this metal, a conductor. We learned that this conductor, it has, if we plot here energy, this is an energy scale, right? If we plot the energy scale, we learned that we have actually electrons filling up all the energy levels up to the so-called Fermi levels. And of course, then there is energy that's necessary, that's going working function for the electron to really come and be ejected from the metal. And that doesn't happen normally. I mean, we not, you know, we have so many objects around and electron is not flowing out all the time. But now let's imagine that we do the following. We apply an electrical potential to this metal. If we apply an electrical potential, we're going to see that from the surface there is an electrical field going on, right? And if we calculate what is the potential, is the electrical field times the distance times the charge. So actually, this normal potential, with as we learn, is the representation of this metal. We are now in a situation that we have a field that's applied, and outside, and we all learned that the field is not zero outside, right? We have this potential. So this is changing the shape of the potential. Because here the potential is like this forever. But now, because I applied a potential, which is represented by this electrical field, so this is the electrical field. So apply an electrical field on the surface of the metal. So by applying this electrical field on the surface, it is possible that the electrons here tunnel out. So they come out, and then you have electron emerging from the metal surface when you apply a potential. That is not giving enough energy to the system to remove electron, right? This is another situation where you give enough energy. We learn with the photon electron effect that if the photon gives this energy, electron comes out. But here it's different. We apply and we had emission. We have a field emission here. So electron can tunnel to this barrier and comes out. So electron that was actually in the Fermi sea here will now be ejected from the metal. And that is an interesting effect that happens, and people use that in electronic devices. So I just explained to you that electron can tunnel and be ejected from the surface. How is this process? You know, you have the electron, you have a kind of width for this barrier, and you have to integrate, because now you have a linear potential, but it's easy to modify this because you know what's the shape of the potential here. So I'm going to apply the transmission, what we learn about the tunnel, which is the transmission to a barrier for particles, and we're going to apply that. And of course, that's the, if you look there, we are rewriting the potential, right? We're going to take as a level, and then we rewrite the potential here, which is W minus whatever is the potential. That's how the potential comes down. So this is actually the potential. Electron can come with energy 0. That doesn't matter, right? Then the potential will expel them. If it is a negative potential, right, then the electron will be expelled. But really the tunneling probability, if we work out, just put the work function and everything, it's just a very nice relation here. Oh, by the way, what is the width for tunneling if we imagine the surface? Here there is no electron, right? Above the Fermi energy, there is no electron to tunnel. By definition, the electrons are occupying the Fermi energy down. So the Fermi energy is the last energy that's occupied in the solid. Therefore, we can just make the potential to be W, and then we get what is the width that we have to integrate. So we have to integrate from 0 to this A, and the A is given by the working function and the field you apply. If you apply a field very tiny, this will have a different slope. If I slow down even more the field, it will come up, up, and up. So that means that a small field makes the tunneling distance bigger. And that's reasonable, because as the field goes down, the slope of the plot goes up. Therefore, this is a straightforward calculation to be done. You just use the expression that we evaluate for the tunneling in any barrier, and that's the barrier we're going to consider, is this rectangular barrier that's made by the surface of the metal and the potential that's applied. And we at the most say, well, electron with the Fermi level will be ejected with 0 energy and then expelled out by the potential. Therefore, we can get an emission probability. Here is the emission probability. Right? It's dependent on the working function, so depends on the metal, and depends on the field. If you apply the field that's zero, this term, if we apply a field zero, means this epsilon is zero, this term is infinite. And we know that the exponential of minus infinite is zero. So there is no transmission. If you don't apply the field, there is no tunneling, there is no emission. If we apply any small field, because of this fact, it will have a smaller probability. And as the field grows, this grows as well. When the field is very large, we can consider this basically zero, and then the emission is probability 1. And this is the probability of emission of the electron. This emission effect is very important in many situations, because sometimes we have a metal, and then we have a isolator, and then we apply a field, and then we can make the electron to tunnel through this dielectric system. Another interesting example is when I have two metal, and I put vacuum here, but that can be a junction, metal, insulator, metal, right? That can be that. And that's a barrier for the electrons of the metal. And we can, of course, deal with this problem, because the electron will not pass through. Nevertheless, because of the tunnel effect, if we put a potential between these two metals, then this is the potential. The potential will make the Fermi levels in one side goes down, and the other goes up, if you want, relative to something. And why is this very interesting? It's because that creates now a whole bunch of levels that are occupied by particles in condition to tunnel. All this, from the energy level of this side to the energy level of that side, are particles that can tunnel. So depending on the field, you may even increase even further this, because increasing the field, this will come even further down. So this is a function. Those electrons that can tunnel, which are the ones that goes from the Fermi energy of this level to the Fermi energy of the other level, correspond to levels that can tunnel. And this, because this was symmetric before, this amount is exactly how much we gain coming here. So that's depending on the voltage that's applied. And the electron will get here depends on the voltage. So the electron will get this energy, the electron charge times the applied voltage, as energy from one side to the other. And this is a very interesting tunnel effect that is applied in many situations and many devices. And there is a characteristic current, because if the electron will tunnel, the tunneling of the electron will produce a current in the circuit. And there are very nice characteristics of the curve of the current versus the applied voltage in this situation. And of course, if this is very big, we know the tunneling will be small. But if this is on the angstroms type of nanoscale, right, type, then we can have a very nice junctions, metal, insulator, metal junction, and then we can have a very interesting tunneling effect, depending on the voltage. And then we can use that as controlling current as a function of voltage, using this quantum effect. So this is an interesting basic phenomenon that we apply for many, many devices, many electronic components, in fact, can have this tunneling effect. Nowadays, with the nanofabrication of things, this is even more frequent, because we can do nanostructures, metallic structures, intercalated with nano isolator structures. And then the electronic characteristic with this, which is basically how much current I pass as the voltage, so we can do interesting elements. And the transition here is basically given by what we already explained to you in the last example of the tunnel by applied field in a metallic surface. And this is very sensitive to the tunnel distance, or the distance between the two metals here, right? So people can do all kinds of structure between two metal, putting different distance, varying distance, making all kinds of things. And then with this, and with the different metals, because the working function depends on the metal, you can play with the tunneling effect, with the tunneling probability. And you can make this harder or easier, and making control of the current by applying field, which is basically what we do in electronics. Electronics is a game of applying voltage and having controlled current, and to do all kinds of things. So this is an interesting example, and is applied in many electronics, and in also some other systems where we apply voltage and there are metallic elements involved. There are some ideas of doing this kind of thing for osseointegration of metallic implants and things like this, but we're not going to discuss this now because it's still very exploratory. Was a nice example, but I want to move on to other example, the nuclear decay. This is very much interesting, and we know that radiation is very much involved in biomedical engineering, especially because the radiation is the main physical element of a lot of therapies, like the radiotherapy for cancer or for other diseases. And so we normally rely on X-ray that's produced, or sometimes in the spontaneous decay of nucleus of different isotopes of atoms. So we're gonna do here to show to you how things comes out, how is this transformation of atomic nucleus by the radiation, by the radioactivity decay, I'm sorry. So this is what we call a natural radioactivity. And radioactivity, you know, was very important discovery of Madame Curie. She got a Nobel Prize because of that. And we're gonna explain to you here now how that happens. And normally what's happening is, in the inside the nucleus, you have protons and neutrons, as we all learn, right? If I have too much protons, they try to repel each other. And then there are other forces involved in the nucleus. When you are in a very short distance, like the nucleus, particles have different types of force. That's not the electromagnetic force. So even though proton repel proton, there are attraction between them too, by what they call the weak interactions in the nucleus, in the nucleons, between the nucleons. So that makes the nucleus of the atoms to stay stable. But you have always a kind of competition between the nucleus wants to stay together because of those different forces that we didn't learn yet, and the repulsion of the protons. So when we increase the number of protons and the number of mass, which means increasing the number of nucleons, protons and neutrons, it turns out that sometimes the repulsion between protons, they prevalence over the other interactions. And then the nucleus is unstable, and it may decay, expelling part of the nucleus. And there are a very traditional way of doing that, is expelling, either converting a proton in a neutron and expelling an electron. This is called the beta radiation or the beta decay, or expelling two protons together with two neutrons in a particle of mass 4, and that's called the alpha decay. alpha decay is something interesting because the nuclei, or the nucleus, sorry, emits 2 protons together with 2 neutrons bounded together in this alpha particle. So we say that the alpha particle is like the nucleus of a helium atom. And this particle emerges from the nucleus. Decreasing the size of the nucleus, especially decreasing the mass and the number of protons, you increase the stability. So that is this what we call natural sequence of decays of non-stable isotopes where the nucleus decay. And they are emitting, like uranium, radium, they are all emitting particles and became more and more stable. But the idea is how those particles come out from the nucleus, right? And that's where the tunneling comes about. Because something is keeping the potential that keeps the nucleons, which is the name of protons and neutrons, in the nucleus. They must be something strong and keep them together, because we know that matter is quite stable. But on those situations, they may have a chance to tunnel. And if they do tunnel, because of these instabilities of the nuclei, then there is emission of the alpha particle. So let's treat this on the view of the tunneling that we learned in the last lecture, in this lecture, and we keep learning. So the way that this happens is that to make the nucleus more stable, a part of it goes. And the way that is minimize the energy, and we can find that in any introduction to nuclear physics, is emitting the alpha particle, which has mass 4, charge plus 2. So normally we call the particle plus 2 for the mass. This is the alpha particle that comes out. And the particles are inside the nucleus, and they are there kept by a potential, a physical potential. Otherwise, they will leave. So how is this physical potential? It's like a bag, or it's like a well that keeps the particle inside. Normally, there is many models for these nuclei. One of them is called MIT bag model, very famous model that says that it's like a bag. And the bag is there, the particles are there inside, and makes the nucleus to exist. So in this region, the alpha particle and many other particles are there. And then suddenly the particle has some energy, right? Because this is a collection of energy inside. And if you look how the particle looks, and the whole nucleus has a charge. So when the alpha particle leaves, it feels a potential that's like the repulsion by the Coulomb interaction. So actually that is outside. Inside the nucleus is like a bag, like a square well. We're going to come back to those bound systems in the next few lectures. But this determines the size of this bag that keeps the nucleus has a dimension R0. And the particle now has a chance to tunnel, because this is, if the particle exists by fluctuations of the nuclei and gets some energy, there is a chance to come and be ejected. And of course will be ejected and will get all the energy that this repulsion are able to give. So the energy normally is equal to the kinetic energy that's coming out. Okay? So inside the nucleus we can imagine to have those alpha particles, and they don't have energy to bypass the barrier. They don't have to, like come to the top and fly out. So they will rely in the tunneling effect. If they can tunnel to this barrier, because this is the potential that we are seeing for the alpha particle. Inside the nucleus is bounded, and then if it comes out, there is this repulsion, as I told you, because of the electrons, the charge of the nuclei. So this is the Coulomb repulsion. And then there is a chance of tunneling. You know, just to imagine, we can imagine like the alpha particle is oscillating. We're doing a classical picture here. And this is spherical, right? We all know that the nuclei is spherical, so we're putting this in radial coordinated. So if we imagine the alpha particle to have to oscillate inside the nucleus, the frequency of oscillation is given by the possible velocity and the traveling time. So the frequency between coming and going back is right, but you have to remember that if you look in the this is in radial, so actually the travel inside the nucleus is 2r0, and the particle can come to one side or to the other. So the frequency that the particle finds the wall and finds the conditions to tunnel is v divided by the dimension, right? V is the velocity. The time that takes for going from one to the other is just 2r0 divided by v. So that should be the time in between possibilities of tunneling. If you invert that, that's the frequency. That particle has a chance to find the wall and eventually tunnel and escape. Now, if you take in account the size of the nuclei that we know that's 1 over 10,000 of the size of the atom, so it's about 10 to the minus 14 meters. And the velocity of this particle by the typical energy, we get a frequency that goes around 10 to the 21 per second. That's the oscillation. And in each oscillation, in each 10 to the minus 21 seconds, there is a chance of the particle tunnel. So in each oscillation, the particle finds the wall and can tunnel. That's the model we create here. Now, we know exactly the potential. We know exactly the shape of the potential that we must tunnel. And we know the distance that has to start and the distance that has to end the tunnel, by giving some energy, which will be the kinetic energy. That energy will be converted in kinetic energy after you leave, after the particle leaves the nucleus. We therefore use the expression we got before. Remember, we calculated that the expression to calculate the probability of tunnel is the integral of this kx, and this kx is just the potential minus the energy root square multiplied by 2m over h bar square to the 1/2. Actually, we wrote in previous lecture as root square of everything here, but here I separate to be elegant. Okay, then we know the potential, we know everything. We know r0, which is the size of the nuclei, and we know the r, which is the matching of the potential with the final energy. So if we're gonna end with this kinetic energy, it's just make it equal. This to this, we get r0. If this is equal to k, the kinetic energy, that the particle will emerge, that's the kinetic energy, then we get what is r0. So that's simple, it's not hard. Easy to do the calculation. And easy to do the integral as well, because integral to 1 over x, we all know that is what it is. Right? Okay, so we're gonna do this integral then to calculate what is the tunneling probability for an alpha particle to comes out from a nucleus. And we make some consideration. We know that we're gonna tunnel to a distance that's bigger than the size of the nucleus. And we take the integral, and we do the logarithm, because the probability is exponential. So when you take the logarithm, we get the expression. So this is basically the expression of the integral. Time is -2. So we can get that the probability for the particle to emerge with some kinetic energy K, given that the nucleus has a size R0 and has a positive charge, which means the number of protons, Z. Z is the number of protons. R0 is the size. And K is the kinetic energy that the particle emerges from the nucleus. So we have this. If we multiply this probability by the frequency, we have the rate in which particle is coming out. The rate in which particle is coming out is a time, right? Oh, the rate is the rate. The inverse of the rate is the time that normally one nuclei will eject one particle. This is related to the lifetime of the nucleus. If this is millions of years, the nucleus is very stable. If this is hours, the nucleus is very unstable and is very radiative, has a lot of radioactive activity that is measured for many different ways and everything. That biomedical engineer normally, and engineer in general, knows how to do. So the rate, which means how many decays I'm going to have per unit of time, is the probability times the frequency, which is given by this quantity. But I already calculated that quantity. So by taking the logarithm of this, I get the logarithm of f plus the logarithm of p. And I can measure that. I can go in the laboratory, take different radioactive elements and measure. And measure as a function of the energy that comes out. And I multiply by the charge of the nucleus. And I get many experimental points, and these points make a line with a slope. You see, I count the decay, and I see, I measure the rate, and I took the logarithm. It's something that you have to do in the lab. And there are counters that do that for you. And what we got is a straight line in this plot. This is a log of the rate as a function of the atomic number or the proton number times the kinetic energy that the particle was expelled to the -1/2. And if you follow this relation that we deduce, this is exactly this term here. Because the rest of it are kind of constants. The only thing that appears here is this dependence. So by measuring how many nuclei decay per unit of time, and that allows us to get the rate, we get the slope, and the slope is exactly what was calculated by the tunneling considerations of this system. And the number of decay normally goes that way, because the dN dt is basically equal to the probability times the number, right? So if you do the integration, you get that the number of nucleus that decay is given by this expression. And this gives you the lifetime of the nucleus, because 1/tau is in average how long it will take for the nucleus to decay, and that's the lifetime. So you see, all this based on tunneling. So tunneling is quite important. I'm going to give you some applications now of tunneling. And I'm going to start this lecture, give you the application of the electron tunneling microscope. The electron tunneling microscope is a wonderful device where we have a metal surface or any surface, metallized, and we come with a tip. So this is the tip. And we we come with this tip, and of course there is a gap here. There is a barrier for the electrons. I apply a voltage, and then I would have a current, but I have a barrier, vacuum, nothing, that do not allow my electron to go. But that is the tunneling. The tunneling is able to make the electrons to come. And you remember, to keep the flux, I have to keep the distance. So what I do is move the tip around, and then I fix it, the current. I move and I go up and down with the tip such that I make constant current, tunneling current. And if I make constant the tunneling current, is like making sure the distance between the tip and the surface is always the same. So by moving the tip and making sure the tunneling current is kept constant, I move it to keep the current constant. And what I do at the end of the day, I map the pathway of my tip. The tip is going that way, let's say. I'm moving the tip. But I'm going up and down in a way to keep the current. And if I do that, the motion of my tip maps the landscape of the surface. And the tip is made in a way that ends in one atom here. So this is, technology allows us to do that. And then, the tunneling, as we remember, the tunneling depends on the potential, but depends essentially on the distance, on the distance between these metals. And therefore, what we do is, we keep the current, we keep the distance, keeping the current, because this is what the tunneling relation gives us. And when we do that, we just map. So you see, this is the current that was measured. Or this is the pathway of the tip to keep the current. And when we do that, we get exactly, the landscape of the surface. That's the principle of the tunneling microscope, widely used in biomedical engineering and all the engineering and all the bio anyway. So we know what's the surface, and this has a very high resolution because this is very sensitive to this. So even if there is one atom step on the surface, and I move my tip up to keep the current, I measure the size of one atom. And there are, of course, technology to measure this using optics, interference, and everything. So this is an example of a molecule that's on the surface of some other material, and you're doing these tunneling microscopy images, and as you can see, you can start to see the real electronic distribution of this, and with some improvement of the technique, you can actually see the rings of carbon here, with some specific points like this group here, hanging around so it's fantastic because we actually can see molecules in a surface of the materials. So this is one of the applications, but we have many others, as we're going to see in the next lecture. See you.